Hello. So today what we're going to do is we're going to review just a little bit about the covalent compounds and the acids, the naming parts, and then we're moving on to balancing chemical equations and our what we call stoichiometry. Now, for our covalent compounds, remember that this is when we have just our nonmetals, so we don't have any metals with them. And what we want to do is we want to look for whichever one has the smallest group number. So we're kind of looking at who's going to be the most like a metal. So the one farthest to the left is normally what we start with. Now, if they end up in the same group, then we write the element with the greatest row numbers, the one farthest down first. So most like a metal is really what we're going for. So that's why if we have carbon and oxygen together, carbon is in group 4A, oxygen is group in 6A, and so we start by writing out the carbon first. Right. Now from there, instead of using our ionic charges to figure out how many we have, because covalent compounds don't work like that, we have to instead indicate the number for each. So we use a prefix system, and these are the first 10 of those prefixes, so we want to make sure that we know them. And so we're going to use mono to indicate 1 or di to indicate 2. And so in some ways, covalent compounds are easier to name because they include the number of each atom. In other ways, they're harder because we have to remember all of those prefixes. So it just kind of depends. So if we're looking at something like CO2, we would call that monocarbon because there's one carbon, and then dioxide because there's two oxygens. Now for the very first element only, if there's just one of them, we can actually get rid of that mono and we can just call it carbon dioxide. Now, that doesn't work for the second one. So if it's just C and O, we wouldn't just call that carbon oxide because that would imply it's an ionic compound. So instead, we call that carbon monoxide. We still use that prefix for the second one. And so we can't omit this mono. We have to include it there because the second one, we have to indicate that there's only one of those oxygens. So you write the name of your first element, include the prefix of it, and then you write the name of the second element, include its prefix, and change it to "ide." Right? And there we go. So let's take a moment and let's fill that in for these compounds here. So we're looking at them. We're looking to see if they're nonmetals. So sulfur and bromide both are nonmetals, so it's going to be a covalent compound. Now there's one sulfur and one bromide. So we can write that as sulfur bromide. Now we can't just leave it as bromide, so we need to actually change this to mono bromide to indicate that there is one of them. So for this one, we're going to do this, sorry, not with 2 oxygens, but with 4 oxygens. And so we should have that as dinitrogen to say that there's 2 nitrogens. And then we should call that as tetraoxide because there's 4 oxygens. For this one here, we have phosphorus hexaoxide. That means that there's 1 phosphorus. Hex stands for 6, so there's 6 times of oxygen. And so our formula should be PO6. This one, we have 2 arsenic. We have 3 sulfurs, so that should be diarsenic, trisulfide. And then on this last one, BF3, we should have this as boron trifluoride. So pretty straightforward in making that conversion. Now, when you start to see hydrogen mixed in with your nonmetals, then it can get a little bit more complicated. And for this, we need to be looking at whether or not we have an acid or not. Now, acids are fairly easy to identify in that we're looking for a hydrogen that starts this off. And that's how we're going to identify our acids for now. So for something like this, if there's just two elements, so it's hydrogen and just one other element, then you want to first start off by writing hydro. You then name the other element sulfur. You add in an ic to the end, or sorry, you change the ending to an ic, and then you add in acid. So if this was something like HCl, we would start that with hydro. Then we would add in chloride or chlorine. We change the ending to ic. So instead of chlorine, it becomes chloric, and then acid. Okay. If it's not just an element, then it means that we have a polyatomic ion there. So we have to look on the periodic table or on the equation sheet. We're looking at a list of polyatomic ions, and we're trying to find ClO. Now, ClO3 is chlorate. And so we don't have to use hydro anymore. Instead, we just start with that polyatomic. Now, if it ends in an 8, it goes to an ic. If it ends in an ite, it goes to an us. So in this case, we have chlorate. So this becomes chloric, and then it finishes with acid. Down here, this is acetate. So that becomes acetic. Right? We change the 8 for an ic, and then we end it with acid. And so that's how you can kind of tell the difference between them. And so I'm going to show you a series of compounds that we're going to practice identifying. So for one of them, what we're going to be looking at is H3N, HNO3, and HNO2. So their names are very similar. And what's going on here is H3N. Now that's just our nitrogen and a hydrogen. So we should start that with hydro. Instead of nitrogen, we should change that to nitric acid. HNO3, that's a polyatomic ion, and that's nitrate, so that becomes nitric. And NO2 is nitrite, so that becomes nitrous acid. And so that ending allows us to change each of those other things. Now, sometimes you might get more complicated polyatomics. You might have something like this, which is perchlorate, but the rule is still stay the same. So if it's perchlorate, we still only change that ending because it still ends in ite. So this becomes perchloric acid, something like this, HClO. Normally that's called hypochlorite. We still follow those rules. We can leave that hypo there, and this becomes chlorous acid. So that's how we name our acids. Now, moving back, we're going to start to elaborate a little bit more on our chemical formulas. Now, remember, chemical formulas, we either show those up as empirical or molecular ones. So their goal is that they're going to give us the, so a chemical formula, when we combine it with the molar masses of its element, they tell us the relative quantities of each element in the compound, which is really useful. So we can find that in a couple of different ways. Now, chemical formulas are innately in the relationship between those atoms and molecules. And so for some of them, we can say, like, if we have CCl2F2, we know that 1 mole of that compound has 2 moles of chlorine atoms inside. Because we can see the pieces inside of it. In the same way that if we had one team of basketball players, we would have 2 forwards, right, or 2 players that play forwards traditionally on that team. These relationships can then be used to determine the amount of each element or molecules. And so that's what we call a percent composition. So when we're looking at percent composition, one of the common ways that we do that is by mass. So for a compound, we can determine the percent of each element in that compound for its mass percent. Now that can be useful in determining the formula of the compound, or they're from an experiment where we can just determine which elements are present and their mass, kind of like what we did with our lab. And sometimes those percents don't always add up to 100. They should be really close to 100, but sometimes there's a little bit of variation depending on rounding and our detection limits. So how you find the mass percent of that element is you find the mass of element X inside of one of those compounds, and then you find the molar mass of that compound, so the mass of 1 mole of it. Once you have that, then you will multiply that by 100. So if we wanted to find out the mass percent of hydrogen in H2O, we would take that hydrogen, we'd find its mass, so 2 times 1.00794. And we would add, and we would put that over the total molar mass, which is 2 times 1.00794 plus oxygen, 15.999. And then we multiply that whole thing by 100%. So now you end up with something that's kind of like 2 over 18 times 100%. And so if we had done all those math, or done that math and kept those values, we would get something like 11.19%. It's 190 if we're looking at our sig figs. And that's how much of the mass of water is made up of just the hydrogen. So let's try that. How many hydrogen atoms are present in 25.6 grams of urea? The molar mass of urea is 60.06 grams. So we have the entire compound, and we want to know just how many hydrogens there are. So we want to think of our plan here. So we're starting with grams of urea, which is NH2CO, and we're trying to get into hydrogen atoms. So anytime we have this, if we have the grams of it, the first thing that we want to do is we want to move that into moles. Because if we can move that to moles of NH2, then we can move that into moles of hydrogen. And then once we have moles of hydrogen, we can get to our atoms. So that's going to be our strategy, is how we can move that. So we should be thinking, how can we figure out how many moles there are? And then we should be thinking how we can figure out how many atoms are inside of that mole. So we took that 25.6 grams and we've changed it to moles by using its molar mass. Now we know that for one NH2, there's really 4 hydrogens there. So one of these molecules has 4 atoms of hydrogen inside. So that means 1 mole of that compound is 4 moles of hydrogen, like what we have here. And then we can use Avogadro's number to convert those moles into atoms. And so this is how many atoms it would contain. Now our empirical formula is one of the ways that we start to see this get developed. And that's because empirical formulas are just our lowest ratio of those elements inside. So it's when we don't know exactly how many molecules there are, but we know how many of each element there is. Now, why this happens is when we do experimental work, we might just find that percent composition. So we might be able to tell, oh, there's this much of this element, there's this much of that element, but we might not be able to tell how many of those molecules we had broken apart when we did that experiment. So in order to find an empirical formula, what you want to do is you want to take those mass percents that they gave you, and you want to go ahead and turn them right into grams. So if we had told you that there was 25.0% of lithium in the compound and 75% of oxygen, what we want to do is we want to go ahead and assume that there's 100 grams of that compound. that would tell me that there's 25.0 grams of lithium and 75, we'll put 0.0 so we can line those up, grams of oxygen. Now that they're in grams, we can convert them into moles so we can compare them. So we can divide by their molar mass for each of them. And so we can use our 6.94 grams per mole of our lithium and our 15.999 grams for our oxygen. And we can change these to our moles. Now, the reason why we want to get them to moles is because if we're looking at their chemical formulas, that's always based on their atoms in comparison to each other. And so we can't use their masses. That mass ratio is not going to be the same ratio as their chemical formula, but the mole ratio will be. Now that we have them in their moles, we're going to divide by the smallest one. And what that's going to do is that's going to set it equal to 1. So in this case, if we divide by lithiums, so 3.60, that would say, like, if there was only one lithium atoms, we could figure out how many oxygen ones we would need. So we could take that 4.68, divide by 3.6, and also get 1. Sorry, not 1. We get 1.30. Now, what we're trying to do is now convert that ratio into a value there. If it was within 0.1 of a compound, we would just be able to round that up because there's a little bit of variation that happens when we're measuring these things naturally. So if this had been 1.9, we would have been able to say that that was lithium and 2 oxygens. But because it's not, then we have to change that. So 1.3, we're trying to find something that's close to it, something that would make that number a whole number to get rid of it. And so some of those common ratios are down here. If we have a ratio of 0.5, if we multiply all of it by 2, that becomes 1, right? And so if we have 0.3, if we multiply everything by 3, our lithium would go up to 3, and our oxygen would go up to 3.90, which we could then round. And so we could have lithium is 3 and oxygen as 4 for something that had this molar mass breakdown. And so that's what we're looking at there about how we can convert those. So these are our 3 most common ones, 0.25, 0.33, 0.5, right? And you can kind of think of them as being fractions. 1/2 is where that 0.5 comes from. 1/3 is that 0.33. And so that's how we're trying to get rid of them, is if we multiply 1/2 by 2, we would then end up with a whole number. If we multiply 1/3 by 3, we end up with a whole number. So that's how we're getting rid of them. Once we have an empirical formula, the way that you find the molecular formula is the molecular formula is always equal to the empirical formula times some number n. And that n is always going to be a whole number. So to do this, there's kind of a relationship that has to develop. And that means that the molar mass of that whole compound, when we divide it by the empirical formula's molar mass, it's going to give us a ratio there. So let's say that we have N2O4 as our compound, but we don't know that yet. We could find its molar mass. We might know that our molar mass is 92.02 grams per mole. And the empirical formula is going to be NO2, 1 nitrogen and 2 oxygens. Now that empirical formula would be 14.01 plus 2 times 16.00. So 46.01 grams per mole. And so this gives me a ratio of 2. So my N is 2. So now what that tells me for my molecular formula is that it's 2 times our NO2. So our molecular formula is N2O4. And so that's how we're able to find those molecular formulas. We use that ratio of the molar mass, and that molar mass we might find experimentally. It might be given to us. We might also just know the moles of something and the amount of material, and then we can figure out its molar mass from there too. And once we know that molar mass and we know the empirical formula and its ratio, then we can find this N value and turn that into its molecular formula. This really shows up often in combustion analysis. And the reason for that is we take all that combustion, or we take that sample, we heat it up, and we decompose it with oxygen. And so all of the carbon, we'll find out that's in there, shows up as CO2, all of the hydrogen as water, and all of the rest is oxygen that can be left over or put in. And so that's how we find empirical formulas, because we only know how many elements of each there were. And then once we have the empirical formula, we can sometimes find the molecular formula. And so that's kind of what's going on here. So as an example, we have an organic compound Z, and it's made up of carbon, hydrogen, and oxygen. Or sorry, carbon and hydrogen. Now, we would like to figure out its molecular formula based on this information. So we want to look and try to find out how much carbon there was and how much hydrogen there was. So CO2. Now CO2 has a molecular mass of 44.01 grams per mole. And I found that by taking carbons 12.01 and 2 of my hydrogen, or my oxygens, to figure out that molar mass. So our compound there gave out 8.8 grams of CO2, which is 0. And then I have this as 20 moles of CO2, which is the same as saying 0.20 moles of carbon. H2O has a molar mass of 18.02 grams per mole. There's 4.5 grams of H2O. So that's giving me 0.25 moles of H2O. Now remember, there's 2 hydrogens for every mole of H2O, so that's really 0.5 of hydrogen. All right. So now I'm going to clean this up a little bit. We have 0.20 moles of carbon. We have 0.50 moles of hydrogen. And so we're going to start to divide by our lowest ratio, 0.20 moles carbon. And that's going to set this one equal to 1. And this value, 0.5 divided by 0.2, becomes 2.5. It's like really 2.497, which becomes 2.50. And so we want to get rid of that 0.5. It's too big for us to just round off. And so we need to change this. So this should become carbon to hydrogen. So multiplying both of them by 2, 5. So this is our empirical formula. But we still need to find our molecular formula. So we know that the molar mass is 58.124 grams per mole. And so we need to find the empirical formula's molar mass, which is 29.0597 grams per mole. And so we can see that this is our N value of 2. So our molecular formula should be 2 times C2H5, so that's C4H10. So this is our empirical formula. This is our molecular formula. Okay. So the big part to practice is making sure that you can find those formula masses. We need to find those molar masses as we go through this because it's going to be really useful as you're going through that part. There's another percent composition practice. This is where you guys can look at each of those different amounts of the material and you can start to break those down. And so that's what's going to happen on these next couple of slides. So for this case, we want to calculate the percent composition of our H, our P, and our O in our phosphoric acid, so H3PO4. Right? And so I'm going to leave that slide there. It's going to give you your breakdown kind of step by step for that next couple questions, but we're going to go ahead and move on. In the same way that you should practice finding the empirical formula for this ascorbic acid as well. Make sure that you practice some of those. They are a little bit tricky, and so you want to make sure that you're working through those problems. The next part that we're going to get into is kind of our chemical reaction parts. So for our chemical reactions are when we convert our reactant material, some old material, into a new substance with different compositions and different properties. Now this happens for a variety of reasons, but the model that we're going to go with right now is going to be called this kinetic molecular theory. And so this idea is that at any temperature above our absolute zero Kelvin, our molecules are in motion. They have some amount of kinetic energy in them. That's actually what temperature is measuring, is that average kinetic energy of them. So they're moving around in random directions. Now, as they're moving around, gases move the most because they're not bound together so tightly. Liquids move the second and solids the least. But as they move around, they can start to collide with each other. So kind of like a car accident, right? They can run into each other. So they're playing bumper cars. Now, as the molecules move around and they collide with each other, it depends, well, that collision will depend on the speed that they're traveling with, and the different concentrations depend on how often they make those collisions. Now, when two molecules collide, a certain amount of energy is produced. And if they're moving fast enough, then that collision can produce enough energy to create a chemical reaction. So a chemical reaction always starts off with either forming a new chemical bond or breaking a new chemical bond. And so it takes energy for us to break those chemical bonds that hold them together. The activation energy is the minimal energy for that reaction that's required for it to start to transform into its product. So it's kind of like the amount of energy we need to get in before it starts. So later on, when we start drawing out these diagrams, they kind of look like a hill. And that hill could be going down or it could be going up. But that top of that hill is our activation energy. It's the highest energy that we need for that pathway. And it's kind of what prevents a chemical reaction from going on all of the time. If there was no activation energy, then our materials would constantly be going from reactants to products, as long as those products have a lower energy. Now that activation energy kind of acts as that hill, as everything tries to kind of stay as they are until they at least break over that hill. And so this is a visual kind of that chemical reaction motion. So we have a hydrogen atom there in white, an oxygen molecule is in orange, and now they've collided. So if they're moving fast enough, then they have enough energy to break that bond. So that's what's happening with this collision. Energy there. And that was able to separate them into that water molecule. Now we have water, more collision. That's how we're going through our chemical reaction, trying to transfer from our reactants, that hydrogen and that oxygen, to our products. So that's what's going on in this arrow in the middle. Okay. So our chemical equations are kind of a shorthand way for us to write them out. So they should provide us with several things. One is it should always include all the formulas of our reactants and our product. It should include the states of our reactants and our products. And the other part that we're going to do is it needs to have the relative numbers of how much reactant and how much product was used. So it's kind of our recipe for making that compound. It has to include not just your ingredients, but it's also got to include how much of your ingredients. And once we have that, then our chemical equations are really important in determining the masses and weights of our products that we need or products that can be made. So, sorry, reactants that we need and products that we can make. So when you first get this, the first steps that you want to practice is making sure that you can identify the reactants and products in the words, place them in the proper relationship compared to the reactant arrow. Then you indicate their states. You can then turn them into their compounds, the compounds into the chemical formulas, and then our last step is going to be to balance them. So this could be an example of how you might get a question. Hydrogen gas reacts with oxygen gas to produce liquid water. Now, we know that hydrogen gas is a compound, oxygen gas is a compound, and liquid water is a compound. So hydrogen gas reacts with, that's going to give us our H2, and it's a gas. And so it's saying reacts with, so we know that we need to add that into our oxygen gas, which is also a gas, to produce, and then our product, water, and it says that it's a liquid. So that plus sign is really anytime we see like reacts with, combines with, is added to, something that's showing that we're starting with these materials, we're mixing them together. There are reactants. That reaction arrow normally takes on the place of something that's to produce, yields, to make, synthesizes, right? Those are all different words that kind of mean our chemical reaction has taken place and we've made new product on the end. So aluminum reacts with lead nitrate to form lead and aluminum nitrate. That means that we have aluminum, which is a compound. We have lead nitrate and lead, as well as aluminum nitrate. So aluminum and lead are both different reactions, as well as our aluminum nitrate and our lead nitrate. So if we want, sorry, for some reason I didn't put a circle around that one. So those are our chemicals that we have going on there. So we want to identify them as being reactants or products. So we know that aluminum is a reactant. We're starting with that. And so the other reactant should be our lead nitrate. Lead, on the other hand, is going to be our product, and aluminum nitrate is going to be our product. So we get our reactants coming together. We get our arrow, then we get lead and our aluminum nitrate. Now for aluminum and lead, we know what state they form when they're in the elemental form. So that's why we have our solids there for them. But our lead nitrate and aluminum nitrate, we might not know, and so we can't add in the states to them. Right? And so then we can leave those blank. If we didn't know what they were, say you knew a little bit, you were familiar with that compound, then you could say that they're solid, or they might be indicated inside the problem. So now that we have this, what we need to work on is we need to work on what we call balancing it. So we're going to do states first, and then we're going to work on balancing them. So the rules for our physical states are that elements that are gases at room temperature are only these ones here. So oxygen, hydrogen, nitrogen, fluorine, chlorine, bromine, and then all of the noble gases. So it's a fairly short list, and that's because it's pretty much our non-metals, and then it's some of our non-metals, and then our noble gases. Bromine is the one tricky one. Sometimes it can be considered a liquid. Sometimes it can be considered a gas at room temperature. It depends on what temperature you're looking at. I believe that the boiling point of bromine is quite low. It's about in the 80s. And so that's why sometimes it's considered to be a gas at room temperature. Sometimes it can be a liquid. We'll take either one unless it's indicated. The only liquid at room temperature is generally mercury for the metals. But sometimes that can also be bromine if you're at like 75 degrees Fahrenheit. Everything else is going to be a solid at room temperature. Now our symbols for that are going to be our G for gas, our L for liquid, our S for solid, and if something's dissolved in a solution with water, then we use this AQ, aqueous. So this is where knowing your nomenclature, the ability to name your compounds, comes in quite handy because you use them often. And if you don't get the right compounds, then it can make your balancing part quite hard. Right? And so let's look at this one here. Solid hematite or iron trioxide is placed inside of a blast furnace with solid carbon and oxygen gas to produce iron metal and carbon dioxide gas. So we should be able to separate out our reactants from there and our products. So I'll give you a moment to do that. Now that we have our reactants and we have our products with their states, let's go ahead and write our overall reaction. And now it wants us to balance it. Now balancing it is what we need to do in our next part. And so before we actually balance this, we're going to talk about what balancing means, and then we're going to come back and balance this one. So remember that we talked about the law of conservation of mass, and that means that for a chemical reaction, neither mass is created nor destroyed. So that means that the number of atoms on the reactant sides must be equal to the atoms on the product sides, and even more importantly than that, the number of each element of atoms has to be the same. So it's not just that the total number of atoms is fine, it can't be 12 and 12. We actually have to have 2 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens, like that. So our first one that we can look at is H2O, the formation of a water. So hydrogen shows up as a pair, H2, oxygen shows up as a pair, O2, and water shows up like that as H2O. Now, right now, as it stands, it's unbalanced there. You can see that while we have our 2 hydrogens as our reactants, we have 2 hydrogens on our products, but we also have 2 oxygens as reactants, and we only have 1 oxygen as a product. So that's not balanced. Now, when you start to balance a reaction, the important part is you can't change these small numbers after the compound. If you change them, you're no longer dealing with the same reactants or the same products. And so if you change those numbers, you get a different chemical reaction going on. It might not be the one you're interested in. So instead, you can only adjust the coefficients that come in front. So that's the big number that comes before it. So if I want more oxygen on the right, I can't just add in a 2 down there, because that changes it from water to hydrogen peroxide, which is a different compound. Instead, I can add in a 2 in the front, and I can add in a second water molecule. That's okay. Now, if I do that, my oxygens are balanced now, but my hydrogens are not. So then I might have to add in a hydrogen back to that side, so 2 of those. And now you can see that we're balanced inside that process. And so that's how you're going to work through and do your balancing. Now, there are also different types of reactions here. There's 4 that we're going to talk about. One is a synthesis, which means to make. And this is when 2 substances combine to make 1. So just like our water example, that's an example of a synthesis, because those 2 hydrogens, they collide with each other to make that water molecule. When we're trying to balance them, we are balancing using those coefficients. And so this is generally the process that I use, where I list out my elements for each. And then I try to work through and how I balance that. So I might change this coefficient here, which would then update my values to 4 and the 2. That means I need more hydrogens on the left, so I can update that coefficient there. And so then when I get to the end, all of my elements are accounted for and everything is matching and balanced. Remember that only the coefficients can be changed. Our second reaction, decomposition. So this is the opposite of a synthesis. It means to break down or decay. And so this is when we have 1 substance that breaks down into 2, or it means that you have more products than you have reactants. So you can have 2 products breaking down, or 2 reactants breaking down into 3 things or 4 things or 5 things, or whatever it is. So this is an example of that. And so what's happening here is that NH3 is getting pulled apart. Those nitrogens pair up, those hydrogens pair up, and we form N2 and 3 H2s. There's also two other ones. So there are two other ones. The first one is called a single replacement. Now, a single replacement means one element replaces another in the compound. So we go from AB to AC, right? So we kick one of those elements out. So that could be something like this with our sodium bromine. And then we swap that out to NaCl. You can also think about this in terms of dancing. It's kind of like when someone cuts in. So let's say that Han and Leia are dancing and Luke comes along. If Luke cuts in, then now Luke and Leia are dancing and Han is waiting on the side. So a single replacement means that one of them is getting exchanged to get a new partner, and the other one stays there. A double replacement means that both elements in the compound switch places, and then we get two new pairs that form. So a double replacement means that everyone changes in the dance. So instead of someone waiting on the side, waiting for their turn to get the dance with the partner, instead both of you exchange your partners, and so then you have two new pairs that form. So this diagram is supposed to be a visual example of each of those four. So we have our decomposition, our synthesis, our single replacement, and our double replacement. So you want to go through and try to identify those, which one corresponds with which. And we should have these identified like such. Now your book also takes your synthesis and sometimes calls it a combination reaction. Those mean the same thing, they're just two different terms. So for our balancing of our chemical reactions, we should now be able to practice this a little bit. We should be able to take these and we should work through them and we should practice balancing them. So for an example, our NH3 here with our oxygen, I'm going to write that up on that top. We can do one of these. When I start to do this, I like to list my elements, N, H, and O. So that's all three elements that should be there, N, H, and O. If you don't have the same elements on either side, then you don't even have to worry about balancing. It means that your reaction is wrong to begin with, because there's no way to balance something if you don't have the same elements. So on my left, I have one nitrogen so far. I have three hydrogens and two oxygens. On my right, I have one nitrogen, I have two hydrogens, and I have three oxygens. Now, when you start to balance, there is some tricks to making this easier. And the first part about it is start with the elements that are only in one reactant and one product. So looking at this, the one that I don't want to start with is oxygen. Oxygen is going to be the hardest one to do because it shows up in both products. And so we won't know which one to adjust as we're trying to balance. Instead, I'm going to start with my nitrogen. My nitrogen, we can see that we have one on either side, and so that's good. That means that my nitrogens are balanced. And so what I'm going to do is I connect them, and then I draw a little lock like this. And what that tells me is that those two coefficients are locked in to each other. That means that those coefficients can't change ratios. So if I add a 2 in front of my NH3 for some reason later on, then I also need to add in a 2 in front of my NO2 because their ratios are already balanced to begin with. My next step is I can look at my hydrogens. Now my hydrogens aren't balanced, so I need to figure out what I need to do that. And so if I have a 3 here and a 2 here, the next number that they both go into is 6. So that would be, if I add a 2 in front of here, that would turn that into 6 hydrogens and 2 nitrogens. If I add a 3 in front of here, that turns that into 6 hydrogens. And then that gives me 3 times 1, so that's 3 plus another 2, 4, 5 oxygens. Now, if we go back and we look, we changed our coefficient in front of this NH3. So I also have to go back and change this coefficient in front of my NO2. That changes this to 2. And my oxygen count goes from 1, 2, 3, 4, 5, 6, 7. Okay. And then now the last part that I need to do is I need to balance my oxygen. So my left side needs more of them. It needs 7, but I run into a problem here. If I want 7 oxygens on the left, then I would have to do something like write 3.5 or 7/2 in front of this oxygen. Now for our class, we're not going to do coefficients that have a fraction in them or a decimal. And so instead of doing that, I have to get rid of that 2. And so in order for me to do that, I can do that by by doubling all of those coefficients that we have. So that means that instead of being a 7/2, it's really going to be a 7. And this 2 becomes a 4. That 2 becomes another 4, and this 3 is going to become a 6. And if we go back and we double check, we now have 4 of those nitrogens, we have 12 hydrogens, we have 14 oxygens, we have 4 nitrogens, we have 12 hydrogens, and we have 8 oxygens plus another 6, we have 14 oxygens. And now we're balanced. So our chemical formula should be that one there. We can jump to our next one. This one's going to be our HCl. Plus BaOH2 going to BaCl2 plus H2O. So I list out which ones I have. Nope, I got H in there twice. Don't need H in there twice. And so the one that I'm going to start with this time is going to be my barium. Oh, sorry, I forgot to write in my values. So right now I have 2 hydrogens, 3 hydrogens. I have 1 chlorine, I have 1 barium, and I have 2 oxygen. On this side, I have 2 hydrogens, 2 chlorines, 1 barium, and 1 oxygen. Now I'm going to start with either my barium or my chlorines because we don't see them as often. We don't have them in as many compounds right now. So I might start with my barium. My barium is balanced, so I can lock that in. I can then go on to my chlorine. Now my chlorine isn't balanced, so I need to put a 2 in front of this. That changes this to a 2. That changes this from a 3 to a 4 as well. And now that is locked in. From there, I can now look at either my hydrogens or my oxygens. In this case, I'm going to look at my oxygen because my oxygen only shows up in one compound. And so I need 2 oxygens, so I need to put a 2 in front of here. And that changes this one to a 4. And now, when we look at my hydrogens actually end up being balanced already. So I don't need to change anything about them. And sometimes that's why we save those complicated ones to last, because sometimes by the time we get there, based on everything else we've done, it's already balanced itself out for us. And so now we're balanced. We have 2 HCl, 1 barium hydroxide, 1 barium chloride, and 2 water molecules. We'll do one more example of this here. This one's a little bit more involved. NH4, 2, SO4, plus AlCl3 going to Al2, SO4, 3, plus NH4Cl. So before you watch me do this, I would really recommend that you practice going on through this on your own. because that's really what we were trying to practice here. Oh, there we go. Got this thickness back. So we have a lot of elements this time. So we have to go through and we have to write in how many. So we have 2 and 8 and 1 and 4 and 1 and 3. And then we have 1, 4, 2, 3, 12, and 1. So think about which one you want to start with. For me, I'm going to start with my aluminum. I'm going to go ahead and put a 2 in front of that. That would change this to 2 and this one to 6. And I can lock that in. Then I might move on and do my chlorines. Now that makes this have to be a 3. And if that's, or sorry, not a 3, it needs to be a big old 6. There we go. So that becomes a 6. Then my nitrogen gets to become a 6. My hydrogen becomes a 24. And then everything like that is balanced. I could then possibly look at doing my nitrogens next. So in this case, I would need a 3 in front of this, because that's going to change that nitrogen to be 6. That also changes my hydrogen to be 24, my sulfur to be 3, my oxygen to be 12. And now as I compare, if I want to move on to my sulfur next, well, that's 3 and 3, so that's balanced. My oxygen, 12 and 12, so that's balanced. And we're going through and all of this checks out. It looks like we're balanced. So that's what we needed to do. Now, in these beginning reactions, sometimes you can get away with a guess and check type of method, where you're kind of just putting numbers in front until it all works out. This method that I show you, it takes a little bit more time, but it's going to let you balance those more involved numbers and those more involved chemical reactions, because it gives you a system as you work through, so that way you can eliminate some of them from others. And so I really recommend that you use a system when you balance. Don't just guess and check, because if you guess and check, when you get into more complex runs, it will become more and more challenging. And so some simple tricks about balancing: choose the right starting element. So start with one that's in only one reactant, one product. Those are typically things like our carbon, nitrogen, chlorine, fluorine, things that we don't see as often. I generally save things like hydrogen and oxygen until the end, because we normally see a lot of them. And then once we have those elements balanced, then we want to keep track of that, so that way we can always keep them in the same proportion. Now, I'm going to put a worksheet on this up online, but there's also a practice that you guys can do using a program called PhET. So PhET is a simulation. I'm going to pull that over here that I'm linking to. And what you can do with this is that you can do a balancing. And so what this does is we can visually see our different materials. So we have our nitrogens here, we have our hydrogen, we have our NH3. And we can adjust how many we have in order to get them to balance. So you can kind of see that right now we're uneven in our nitrogens. We have 1 or 2 on our reactants and only 1 on our product. So I need to add in more nitrogen. So now these are balanced, but now my hydrogens are way unbalanced. So I might need to add in more hydrogens. And when I get them lined up, everything's balanced and we're all set. And so that's how we're adjusting those coefficients. So always start with 1 of each, and then you can go from there to balance. So in this case, I need more oxygen on this side, then I need more hydrogen. Okay. When you're done with that one, what you can do is you can also play the game. The game just has some different difficulties about it. You can still use your tools if you want, or you can kind of be on your own as you try to work through this. So I can see that my oxygens in this case, we have 1, 2, 3. We have 4 on this side, so I definitely need more here. My sulfurs, I need 2 of them. I have 2 of them here. And so when I'm ready, if I think I'm ready, I can check it. And then it lets me go on to the next one. And so that's what you can kind of do. They have different difficulties. You can play on the harder ones. And then it's got a lot going on. And so then you have to work on balancing those as well. And so that's a good tool to kind of practice with as you're going through and doing your balancing. Now, the other part that we're going to cover is what we call stoichiometry. Now, for our stoichiometry comes down to this idea of like baking. It's about what you're going to run out of first. So it's what we call a limiting reactant, or it's about how much product you can make, which would be our expected product or our theoretical yield. So we're going to do our cookie dilemma here. So you're making cookies for a wedding, and you have 6 dozen eggs and 103 cups of sugar. If each recipe makes 2 dozen cookies and calls for 4 eggs and 2 cups of sugar, how many cookies can you make? So you can do batches smaller than 2 dozen. So you can get as small as you want. You can make an individual cookie if you really wanted to. But we want to figure out how many cookies can we make. And so to answer that question, you really have to figure out, well, which ingredient do we run out of first? And then after that, we should also figure out how much left over we have of the other ingredient. So what I've done is I've written out an equation for this. I wrote out the equation for our cookie. 4 eggs plus 2 cups of sugar is going to equal 24 cookies. Now that's not exactly right. We could have other things in there as well, unless we're just making egg sugar cookies. But from here, what we want to do is figure out who is our limiting reagent. So to do that, I take all of my eggs, and I can either take my eggs and turn them into sugar, or I could turn them into cookies, and then I could take my sugar and turn those into cookies as well, and then we can compare. What I've done instead is I've gone ahead and I've taken all of my eggs and I'm turning them into how many cups of sugar they would be. So 72 eggs. Every 4 eggs needs 2 cups of sugar, so my 72 eggs need 36 cups of sugar. Now my 103 cups of sugar, they would need 206 eggs in order for me to use them all. So if we think about that, our 72 eggs only needed 36 cups of sugar, and we have 103. So our limiting reagent, what we're going to run out of first, is our eggs. We're going to run out of our eggs, and that's going to stop us from being able to make more cookies. So our 72 eggs times 24 cookies for every 4 eggs gives us a total of 432 cookies. And so that's how many cookies I can make with the ingredients that I have. Now that means we use up all of the eggs, but not all of the sugar. So we can take those 36 cups of sugar that we need, we can take how much we started with, subtract the amount that we used, and this is how much sugar we have left over. So for a chemical reaction, the limiting reagent is what we call, or limiting reactant to, is the reaction that the reactant that we run out of first. And so it gets completely consumed. So in our cookie dilemma, then it was our eggs. The ones that don't get completely consumed, those are called our excess reactants or excess reagents. And those are going to be, in this case, the sugar, because we have the ones that are left over. The amount of product you can make is called your theoretical yield. And so that was our 432 cookies. That's what our theoretical yield is going to be. We can do a smaller scale example. This is going to be our pizza. So our pizza recipe is going to be 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese. And that's making 1 pizza. And so if we have 4 crusts and we have 10 cups of cheese and 50 ounces of tomato sauce, how many pizzas can we make? So for this situation, we always have to try to get them into something that is the same, something that we can compare them to. So in this case, we can change them all into pizzas. We could have also changed them all into crusts or all into cheese, whatever you want, but we have to get them all into the same unit. So our crusts will make 4 pizzas. Our cheese will make 5 pizzas, and our tomato sauce will make 3 pizzas. So our limiting reagent or limiting reactant for this is going to be the one that makes the fewest number of pizzas. So in this case, that's our tomato sauce. So we're running out of the tomato sauce first, and so that's why we can only make 3 pizzas. So our theoretical limit is 3 pizzas based on the ingredients we have. And then we would have cheese and crust left over. Now, this is more what you will see in our class with our chemical reactions, and so we want to do the same thing. We've given you a reaction up here, and I've gone through and I've already balanced that, but you should always double check, make sure that you're using a balanced reaction. So we have 3 hydrogens and 1 nitrogen, or sorry, we have 6 hydrogen atoms, 6 hydrogen atoms. We have 2 nitrogens and 2 nitrogens, so we're all balanced there. So it's saying that we have 35.0 grams of nitrogen and 12.5 grams of hydrogen. And they want to know how much ammonia we can produce. Now, for us to compare them, we can't just compare their amounts. Because this one here is not talking about them in terms of mass, it's talking about them in terms of moles or in terms of molecules. So we really have to get everything into moles first and then change those into moles of our product. So my 35.0 grams of N2, I should change that into moles. So 1 mole of N2 is 28.02 grams of it. And now 1 mole of N2 makes 2 moles of NH3. And then we can go ahead and we can turn that into the mass as well. And NH3 is 1 mole of NH3 is 14 plus 3, 17 point. 17.034 grams of NH3. And so we can do all of that together. Now, the reason why I like this type of layout is that I can easily see if my numbers cancel out. So my grams of nitrogen cancel out with these grams, my moles of nitrogen cancel out with these moles, and my moles of NH3 cancel out with this. And so we're left with just grams of NH3, which is what we're looking for. To do the math, I multiply everything on top, and then I divide by everything on the bottom. So I can take my 35, divide that by 28.02, multiply that by 2, divide that by, and then multiply that again by 17.034. And that gives me 42.55 grams, right? Or 42.6 grams when we look at our significant figures. Now, that doesn't answer the question by itself. That's just telling me that that's how much I can make with my nitrogen. I have to do that same thing, but with my hydrogen in order to double check which one we run out of, which one is our limiting. So I need to take my 12.5 grams of H2, 1 mole of H2, which is 2.01588 grams. Now I use 3 moles of H2 for every 2 moles of NH3. And so 12.5 divided by 2.01588 times 2 divided by 3 times 17.034. And that gives me 70.42 or 70.4 grams of NH3. So between those two, we know that our nitrogen is our limiting reagent because it made only 42.6 grams of ammonia, whereas our hydrogen made a lot more, made at 70.4 grams. And so that's how we can get to B as being our answer. So we have to convert both of those into the same product for us to compare. You might have thought, well, hydrogen's much smaller in its mass, so we should run out of that first. But that's not the case, and that's because they have different molar masses. Nitrogen needs much more mass because it has a much higher molar mass. And so that's why we have to get them into moles. And then these values here, this 2 and this 1, as well as this 2 and this 3, both of those come from our balanced chemical equations. So we have to make sure that we're balancing in order to get those conversions correctly. They're not always used in the same ratio, in the same way that when we baked our cookies, we didn't use the same ratio of eggs to sugar. So you want to make sure that you're accounting for that. We're going to go into doing one more practice one before we get into that next one. And so the food that we eat, right, it gets broken down and is used for energy. And so one of those, glucose, C6H12O6, we break it down with oxygen to make carbon dioxide and water. So we want to figure out that if you eat 856 grams of sugar, what is the mass of that carbon dioxide that you produce from it? So the first part is we have to double check whether this is a balanced chemical equation. And then we have to develop a way for us to convert our glucose into our carbon dioxide. Kind of like this strategy here. So from our balanced chemical equation, what we can do is we can take that 856 grams of our C6H12O6, and we can convert that into our moles of C6H12O6. Once we have it in moles, we can then convert that into moles of CO2, and we can do that using our chemical equation. And then once we have moles of CO2, we can convert that to grams of CO2 using its molar mass. So we can convert the grams of it to moles. So 856 divided by 180.2, and that tells us how many moles of glucose there was. Then we can use that mole ratio to turn it into moles of CO2. And then finally, we can convert those moles of CO2 into grams of CO2 for that process. And so if we did that all in one step, we get that equation, and that's how many grams of CO2 we would make. Now, it's always nice to double check, try to see if that's reasonable. It makes sense that it should be a lot larger than the mass of the glucose because we are making 6 of them, and their molar masses are not quite 6, and so that's okay. So it does make sense, so we can check that out. Here's another one. All of our alkali metals react with water to produce hydrogen gas. So lithium is working with our water, produce lithium hydroxide and hydrogen gas. How many grams of lithium are needed to produce 9.89 grams of hydrogen? So now we're working backwards a little bit. We know the mass of this hydrogen, and we would like to figure out how much lithium we need. So we should take that hydrogen, and if that's in grams, then we need to get that into moles of hydrogen. Because once it's in moles, we can get that into moles of lithium from our chemical equation, and then we can get that into grams of lithium. So it's a similar step to what we had just done, it's just backwards. Grams to moles, moles to moles, moles to grams. So we can use our molar mass of our H2, we can use our molar mass of our lithium, and we need roughly about 68.1 grams of lithium. And so that's how you take part in that. Now, there's one other term that I want to introduce to that, and that's what we call our theoretical yield and our actual yield. So theoretical yield is what we've been working with. That's how much we think we should produce. Our actual yield is different. So when you bake, not all of those cookies might make it to the end. Sometimes you might drop one, it might fall off the tray, it might get burnt, it might magically get eaten along that path. Who knows what happens to those mystery cookies that get lost? And so if we made 432 cookies theoretically, we might really only end up bringing 420 cookies to the wedding because maybe those other 12 got eaten along the way. You got to do some quality control there, you know? And so that is the actual yield. The actual yield is the amount of the product that's actually obtained from that reaction. So just like you guys did with your zinc and your iodine reaction, not all of that product might have shown up at the end. So our actual yield is how much product you really made, not how much we theoretically would have made. And so you can get your percent yield by taking your actual and you divide it by your theoretical. And then multiply that by 100%. So 100% yield would give you exactly the same value, actual and theoretical. A 50% yield means that you produce 50% less. 150% yield means that you made more. Now, it's possible to have a yield more than 100%. It just means that your product is probably not all pure of that product because it means that you've made more product than you should have. So there's probably something else mixed inside that you weren't expecting, right? Sometimes it's water that has been captured along the way, or you didn't measure out your reactants very well. And so something in there is a little bit off. So we're going to look at an example of this. Titanium is a strong lightweight metal and it's used in a lot of different things. Now it's prepared by taking titanium 4 chloride and we mix it with molten magnesium to produce titanium as a solid, and then we get magnesium chloride as a liquid that we can then separate. And so this is how we purify that titanium. So in the process, they use 3.54 times 10 to the 7 grams of titanium chloride, and they reacted with 1.13 times 10 to the 7 grams of magnesium. And so we would like to figure out how much titanium in grams that would produce. And then secondly, if we only make 7.91 times 10 to the 6 grams, what is the percent yield for that process? So our strategy is going to be similar. Our strategy is still going to be, we're going to take that grams of TiCl4, we're going to change it to moles of TiCl4, and we can change that to moles of titanium. And we're going to do the same thing with our magnesium, grams of magnesium to moles of magnesium to moles of Ti. So we can figure out our theoretical yield, or I guess we should take these all the way to grams of Ti since that's what we're using, because we need to figure out which one is going to be our limiting reagent. Once we have that, then we can compare our theoretical yield to our actual yield to get it the percent yield. So for our TiCl4, we would make 1.87 times 10 to the 5 moles of Ti. For our magnesium, we make 2.32 times 10 to the 5 moles of Ti. So really, our theoretical one is going to be our titanium Cl4, or TiCl4, because it doesn't make as much as our magnesium. So TiCl4 is no longer, is going to be the limiting reagent. And so we take the amount that we would have made, we turn it into our grams, and so this is our theoretical yield. Now that we know our theoretical yield, we can turn that into our percent yield by taking the actual yield, so that's what they gave us, dividing it by our theoretical yield, and that gives us our percent yield. Now, for all of these ones with actual yield, the only way that you can find an actual yield is the experiment must be done. If you are just calculating things, unless you are calculating things with a percent yield given, then you're only finding the theoretical yield. The actual yield is data that has to be collected because something's already been done. That experiment's been completed, that reaction's been taken care of. So generally, your actual yield must be given to you. The only time it's not is if a yield, a percent yield is given to you, and then you can take your theoretical yield and you can use your percent yield to get to the actual yield. So you just want to be aware of those things. Otherwise, generally what you're calculating is only going to be your theoretical yield. And so that's it for today. And so you want to make sure that you're practicing balancing your equations. And then you want to start practicing with the stoichiometry part, because we will start to see a lot of that in this class as we move forward. Good luck.